Algebra 1, Investigation 11. Just like we've done before, we are investigating another type of function. Today it's all about exponential functions, both growth and decay. So we'll just jump right in. Water flows from a crack in the side of a swimming pool, initially releasing 1 gallon of water. The crack continues to widen as water continues to flow from the pool. For every second after that, the amount flowing from the pool doubles. The table below shows this relationship between time and the amount of water flowing. So if we look at this table, we can see at 0 seconds, so when it starts, there's 1 gallon releasing at that time. After 1 second here, then we now have 2 gallons flowing out. After 2 seconds, 4, 3 seconds, it doubles again to be 8. Every time here, we are doubling, so times 2. It says create a graph of the data. So if I were to go down and show this, okay, at 0 seconds, I had 1 gallon, okay, using this as X being my seconds, Y being my gallons. Since my gallons depends on my seconds, it is on the Y-axis, my dependent variable. At 1 second, it doubled, so it was at 2 gallons. 2 seconds, it doubled from there, so 4. And from there, 3 goes to 8, right here. Okay, so if I were to connect these, it would look something like this. Now, that kind of looks like a parabola. It's actually not, though. If we had negative seconds, we would actually see that it would go and follow along like this down towards that x-axis, never touching, actually. Kind of like an asymptote, x-axis, we're not touching with this one. So, number 2, how many gallons of water flow from the pool in the 4th second? If we were to continue this table, we would see that 8 doubles to be 16. And we could see this if our graph was a little bit bigger. We could see at 4 seconds here, it'd be way up here at 16. Okay, it continues. All right, so near the origin, the graph looks similar to a parabola. However, it grows much, much more quickly. The graph models exponential growth. Here's a definition for you. Exponential growth is a situation where a quantity always increases by the same percent for a given time period. Okay, in this case, we're doubling. Okay, so I have 200% of the original, or you could say a 100% increase. Every time we're increasing by 100% or doubling. So to continue on, the stock exchange often shows exponential growth or decay. Sometimes we can show this with a good model. It may not be perfect, just like a scatter plot, we can get an estimate. Okay, but with this one, the annual number of shares S in billions traded on the New York Stock Exchange from 1990 to 2000 can be approximated by the model. S equals 39 times 1.2 to the X, where X is the number of years since 1990. Okay, so create a table of values like the one below, round each share to the nearest billion. So if we're looking at this, I can say after 0 years from 1990, meaning we are at 1990, I am at 39 billion. Okay, at 2 years after that, so I'd say that's like 1992, we would be at 56. Okay, think about how we would do this to find this. X is 2, so I would plug it in and say S equals 39 times 1.2 to the second power. I would take 1.2 and square it, multiply it by 39. And yes, this is something that I would do with a graphing calculator. I would recommend that. Plug in 4, and I would encourage you to stop the video right here. Figure out what these are rounded to the nearest billion. Okay, so take a second to do that. And when you do have it, you will see that plugging in for 4, something like this, 1.2 to the 4th power, so 1994, we would be at 81. Then 6 would be 116 billion, 168 billion, 241 billion next. Okay, so after 10 years after 1990, so we would be at 2000, year 2000, it would be, using this model, 241 billion. It says plot the coordinates, connect the points with a smooth curve. So if I were to do this on my coordinate plane right here, let's see, I need to get all the way to 241 billion. Okay, so my years is still going to be on my x-axis. I'll tell you that time is typically on our x-axis, and y is our money, the billions of dollars. Okay, so I'm going to skip some different amounts here. Let's see, I have 10 boxes. So let's say each box is worth, let's just say 25 billion. Okay, and you can choose what your scale is going to be. I don't have a ton of space here. Maybe you do. Okay, but you can go ahead and label it however you need to make sense. Oop, I messed up. Let me just fix that. There we go. Now that we have this, I'm going to go by ones on my x-axis, just to make things simple. And we would say at 0 years, we are at 39. So I'm just going to do a little bit of estimating here on my graph. At 2 years, I am at 56. 2 years, we're at 56, so right about here. 4 years, we are at 81. So about, let's say right there. 6 years, we were at 116. This is where it starts to really build and go up quickly. 8, 168. So we're all the way up here. And 10 goes to 241. Now, when we do this, since I changed the y-axis so drastically, I went by 25 billion. It doesn't look like that strong of a growth. If this were in an actual setting where each box was one by one, it would be going up ridiculously quickly. It would look something like this. Okay, it would be hugely fast as far as how we were doing this. Okay, but since we changed the x and y, or since I changed the y-axis, it doesn't look as steep as normal. Okay, so we plotted the coordinates for number 4. Use the graph to estimate the number of shares traded in 1997. So that's right in between, like here. We would want 1997. Well, if we're looking at our graph here, that means that I'm looking right here at 7 years after 1990, so about right there. On my graph, it looks like it's below that 150 mark, somewhere like maybe 140, okay, 140. If I were to actually figure this out algebraically, I would plug it into the equation and solve and say something like 39 times 1.2 to the 7th power. Work that out for yourself. Pause the video, make sure you give yourself plenty of time. And when you do plug it in, it works out to be 139.74 billion shares. Okay? All right, so exponential growth is modeled by this function f of x equals k times b to the x. K needs to be greater than 0, okay, so it's never going to be negative. And the percent of growth b is expressed as a decimal number greater than 1. Okay, now we can have exponential functions that are different from those two different qualities, especially that greater than 1. The reason that we have exponential growth is because that b value is greater than 1. We are growing. We have more than, we are actually increasing this. For instance, in this one, 1.2 is my b value. If I were to change this into a percentage, that means that I have 120% of the original. So I always start with 100%, and I must have added 20% each time. So I actually have a 20% increase each year. That's actually quite a bit of increase. It's normally not that big. We can definitely have it happen, but that's a pretty big increase for things like stocks and shares. But it's definitely possible. Now, this one's kind of fun to do. I would encourage you to grab a piece of paper, or we'll need a few for this activity. So it says step 1, take a sheet of notebook paper and fold it in half. So if I were to try this right here, I'm just going to draw it. Here's my piece of notebook paper, and I folded it in half. So here's my first crease. If I fold it in half, then I went from having only one region with 0 folds to 2 regions, 1, 2, when I folded it in half. Now I'm going to fold it in half again. I still have that, so I fold it in half, refold it, and then fold it in half again. Now I have 4 pieces in this paper. If I folded it in half again after that, I would end up with, well, think about it for yourself, fold it, but it ends up, and there's lots of ways to show this as far as a drawing, but I'm going to end up with 8 different squares. Maybe I fold it in half again, all right, ends up with 16. Try this out for yourself and actually fold it. It is actually exponential growth, okay? How about what if we had 3 sheets of notebook paper, okay, and we were to fold them all at the same time? So 1, 2, and 3. So I folded in half. I just made 6 regions. If I fold it in half again for each of these on top of each other, well, 4 in each, so I have 12 regions. Continue folding, we get 24 and 48. Try this for yourself. And especially try this next one for yourself with 5 sheets of notebook paper. Take a second to pause it and see if you get the same thing as I do. If I had 5 with 0 folds, I would have 5 regions. With 1 fold, I would have 10 regions. Another fold would give me 20, then 40, and then 80. Go ahead and plot those points on a coordinate plane. Let x be the number of folds and y the number of regions. Connect the points with a smooth curve. Ends up giving you exponential growth. Yours should come out, and take some time to do this. It is actually exponential. You should have dots all the way up this for your different folds. The data and the exploration are included in the graphs of the functions. For the first one, with just 1 sheet of paper, I had 2 to the x, 3 sheets of paper, and 5 sheets of paper. All 3 functions are in this form that we talked about, y equals k times b to the x. What is the y-intercept of each function? So let's try that. If I had that f of x equals 2 to the x, well, I actually had a y-intercept at 0, 1. F of x equals 3 times 2 to the x, I had a y-intercept of 0, 3. And the last one, 5 times 2 to the x, I had a y-intercept of 0, 5. So where does this come from in the equation? Well, in the second 2, it actually seems pretty obvious. This 3 and 3 relate. This 5 and 5 relate. But where is that 1? It's actually hidden. Remember that sometimes we can show this 1 right in front, and that doesn't actually change the formula at all. We actually technically there have 1 times 2 to the x, which relates to the y-intercept. So whenever we do this, what we are saying is that number before my exponential piece, so the 2 to the x piece, or the 1.2 to the x piece, that number before it is my y-intercept. It's actually my starting point. I started with 1 sheet with only 1 region. I started with 3 regions and 5 regions. Or like we saw before with that the stocks, I had f of x equals 39 times 1.2 to the x. When I started in 1990, I had 39 billion shares. That was my y-intercept, my starting point here. Okay, so how does let's continue on number 9. How does changing the value of k affect the graph of the function? So we just talked about this. Our k value is that starting point, our y-intercept, where we actually begin this data at 0 years or 0 folds or 0 seconds, whatever it might be. So changing the k value affects where we start, our y-intercept. Number 10, as the number of folds increase, what happens to the number of regions on the folded paper? What is the b value for each equation? Write an equation in the form of y equals k times b to the x to model situations where y doubles as x increases. So as we do this, what is in common between each of these? Well, each time that we folded that paper, I doubled the amount of regions. That 2 is considered doubling. So in this case, any one that would double would say something like y equals k times 2 to the x. This would be doubling every single time. Any k value that we start with, whether it's 2 or 100 or a million, if I have 2 to the x, I'm saying that each time that x increases, okay, we double. So, number 11, for any function y equals k b to the x, what does k represent in any situation? When x is 0, well, we talked about this. If x is 0, that means we have a y-intercept. Okay, a y-intercept. So this is all the different growth that we have. We have a lot of different growth, and that k value tells us our initial amount, okay? Our y-intercept, the initial amount, okay? And that b value tells me how big it gets each time. In this case, it doubles. It doubles. All right. So the period of time required for a quantity to double in size is called, literally, the doubling time. And it would be in this form of y equals k times 2 to the x. Just as data can grow exponentially, some data can model exponential decay. We're getting smaller each time. So exponential decay is a situation where a quantity always decreases by the same amount or the same percent in a given period, just like exponential growth. This happens a lot in science with carbon-14. So, with carbon-14 dating, it's used to find the approximate age of animal and plant material after it's decomposed. The half-life of carbon-14 is 5,730 years, which means that for every time 5,730 years go by, I have half of the amount of carbon that I started with. So we're going to find if we started with 100 milligrams of carbon, what is the amount that's left after 4 half-lives? After 4 times, we went this 5,730 years. So how many years are there in 4 half-lives? Well, that would be 4, and our half-life here is 5,730 years. We have it right here, 22,920. So let's find the amount. After 1 half-life, that's 5,730 years. If I started with 100, I want half of that, so 50 milligrams. Another 5,730 years go by, so I have half of 50, or 25. Continue going, 12.5, and then lastly 6.25. So after 4 half-lives, how much of the sample remains? 6.25 milligrams. Once again, think about as you're going through this, each time that I go past that half-life amount, the number of years, I have half of the amount of carbon remaining. This is exponential decay. You can see as I increase the number of years, okay, as years increases, then my amount remaining, my milligrams, decreases. Kind of think, it makes you think of inverse variation. It's not, but it has that same relationship with exponential decay. It's also modeled by f of x equals k times b to the x, but in this case, k is still greater than 0, but we want a b value between 0 and 1. So our b is between 0 and 1, meaning we have fractions or decimals. So a half, like half-life, or maybe you take a quarter of it, or an eighth, or 0.2, whatever it might be, we have it between 0 and 1 is our b value. So since the b is a positive number less than 1, as x increases, the value decreases. So as exponential decay, an exponential decay function can model the amount of a substance in the body over a time. Many diabetes patients take insulin. The exponential function is 100 times 1/2 to the x. Describe the percent of insulin in the body after x half-lives. The half-life of a substance is the time it takes for half of the substance to decay. So, about what percent of insulin would be left in the body after 8 half-lives? Well, if I'm thinking about this, I would maybe make a table for this, saying I have the number of half-lives and the percent remaining. After 0 half-lives, I would still have 100%. After 1 half-life, I would have half of that, so 50%. 2 would be 25. This is looking familiar. 3 would be 12.5. 4 would be 6.25, and we would continue on to 8. I encourage you to continue halving this all the way down, and you will see that by the time you get there, it's actually very minuscule. After 8 half-lives, we don't have a lot remaining. Okay, as far as percentages go, we have, this is rounded a little bit, 0.39% left. That's it. 8 half-lives. Keep having it, and you'll see that we get to 0.39%. So 16, describe the effect the B value has on the amount of substance remaining after after half-lives of X increases. So as we increase this X, we decrease by half, just like the carbon. Each time we have half of the time before with those half-lives. And then we'll just finish up with a couple more questions and matching. Number 17, graph the functions f of x equals 100, 1/2 x, and g of x 50, 1/2 x. How does the k value compare to the y-intercept? Well, the k value is the y-intercept, just like we said before. I would have 0, 100, and I would have 0, 50 for these respectively. So when we look at the graphs of these, I'll just show them. If we had this, here's 50 and here's 100, a very simple graph of this would say our first one, f of x equals 100, 1/2 x. It looks something like this, decaying as we go. And my next one would also decay, but it would hit that x-intercept at 50. Okay? Make sure that you graph those. That's part of this investigation. Go ahead and graph those, and you can see the difference between the two. Lastly, match the following exponential growth and decay equations to the graphs shown. 18. So if I break this down, number 1, I have a y-intercept of 0, 2, and my b value here is less than 1, so I know it has to be decay. Okay, and this is how you would explain your choices. So with number 18, I would be looking for something that has a y-intercept of 0.2 and it's decreasing. Well, I can rule out A. B is a possibility, definitely a possibility. And if we look, starts at 0.2, and after 1, it's half of that. Okay, 0.5 being our decay rate, I would say 18 is B. All right, looking at 19. It also starts at 0.2, but we have an exponential growth here since our B value is greater than 1. So it looks like I'm ruling out A. I'm ruling out B because I've already chosen that one. Graph C starts at 2, and it looks like it's growing quite a bit. And it's true. 19 is C. All right, 20. Now this one looks kind of funny because we don't see that k value out in front, which means that it must be 1. So I must start at 0.1, which looks like, well, between graph A and graph D, graph A fits the bill. Let's see if that's true for all of it. And is it decay? Yes. Our equation shows decay because we have less than 1 in our decay rate. So we would say graph A is for number 20. And let's just check to make sure that 21 is graph D. Do we start at a y-intercept of 0.25? Yes, we do. 2 gives us our either growth or decay. Since it's greater than 1, it's growth, and we do have growth with graph D. Okay, so as you continue through this investigation to finish with those investigation practice questions, make sure you think about all of these different pieces of our function. The starting point and whether it's growth or decay, and how we can show that using a table, using an equation, or using a graph. Well, I hope this helps with your homework and with studying. All right, good luck on these exponential functions.